Before we begin, I kindly request you to subscribe to the channel and click the bell icon to stay updated with our latest videos. If you enjoy the content, please don't forget to like and share it with your friends and colleagues. Now, let's get started. Hello everyone. In this video, we'll clearly understand the Curtius rearrangement mechanism using this visual chart. This reaction converts a carboxylic acid into an amine with the loss of carbon dioxide. Let's go step by step. Step 1. Formation of acyl chloride via thionyl chloride. Let's look at the first step very carefully. We start with acetic acid reacting with thionyl chloride, SOCl2. The carbonyl oxygen of the acid uses its lone pair to attack the electrophilic sulfur of thionyl chloride. This happens because sulfur is highly electron deficient due to the attached oxygen and chlorine atoms. As a result, we form a chlorothioester intermediate. At the same time, one of the chlorine atoms leaves as Cl-, and the proton from the OH group combines with it to form HCl. Now, the chloride ion, Cl-, generated in situ acts as a nucleophile. It attacks the carbonyl carbon of the intermediate chlorothioester. This leads to collapse of the intermediate where the OSOCl group leaves, and this produces acyl chloride, or acetyl chloride. At the same time, the leaving group converts into HSO2Cl, chlorosulfinic acid derivative. Now let's move to the second step, where the acyl chloride is converted into an acyl azide. We take the acetyl chloride formed in step 1 and react it with sodium azide, NaN3. First, understand that the azide ion, N3-, is a very good nucleophile. It has a linear structure with resonance which stabilizes it but still allows strong nucleophilic attack. Now, the azide ion attacks the carbonyl carbon of the acyl chloride. This carbon is highly electrophilic because it is attached to an electronegative oxygen and also bonded to a good leaving group, Cl. So the attack forms a tetrahedral intermediate. This intermediate is unstable, so it quickly collapses. The chloride ion, Cl-, leaves as a leaving group, restoring the carbonyl group. This process is indicated by a double-headed arrow. Final product of step 2. So finally, we get the acyl azide, RCON3, as the key intermediate, and NaCl is formed as a byproduct. This step is a classic nucleophilic acyl substitution. Azide replaces chloride to form the acyl azide, which is essential for the rearrangement step. Step 3. Now we come to the most important step, the Curtius rearrangement itself. We start from the acyl azide, RCON3, formed in the previous step. Thermal activation. On heating, the acyl azide becomes unstable. The key event begins with the loss of nitrogen gas, N2. Remember, nitrogen gas is extremely stable, so its formation strongly drives this reaction forward. Now, this is the crucial part. The reaction does not proceed stepwise, it is a concerted process. As the N2 leaves, simultaneously, the R group, an alkyl group, attached to the carbonyl carbon, migrates to the adjacent nitrogen atom. At the same time, the electrons reorganize. A new NCO system starts forming. Step 4. Hydrolysis of isocyanate. Now, let's move to the next step, hydrolysis of isocyanate. We have the isocyanate intermediate, Rn double bond C double bond O, which is highly reactive because the central carbon is strongly electrophilic. When water is added, the lone pair on the oxygen of water attacks the electrophilic carbon of the isocyanate. This opens up the pi bond of the NCO system and forms a tetrahedral intermediate. Now, inside this intermediate, proton transfer occurs. One hydrogen from the attacking water molecule shifts to the nitrogen. This stabilizes the structure and prepares it for rearrangement. Formation of carbamic acid. After After proton rearrangement and stabilization, the intermediate collapses to give carbamic acid, RNHCOOH. Important concept: this carbamic acid is not stable, it's just a temporary intermediate that will quickly decompose in the next step. Emphasis line: this step is essentially a nucleophilic addition of water to the isocyanate, leading to formation of an unstable carbamic acid. Step 5. Decarboxylation of carbamic acid. Now we reach the final step, decarboxylation. We have the carbamic acid intermediate, RNHCOOH, formed in the previous step. This compound is inherently unstable because it contains both an amine and a carboxylic acid functionality on the same carbon. Why is it unstable? The molecule is set up in such a way that it can easily break down to form stable products, a primary amine, RNH2, and carbon dioxide, which is a very stable gas. Formation of carbon dioxide is the main driving force for this step. Now, the C-C bond between the carbonyl carbon and the nitrogen-bearing carbon breaks. At the same time, the electrons reorganize to form CO2, OCO, and the nitrogen picks up a proton from the medium or internal transfer, forming the amine, RNH2. This happens very rapidly, often spontaneous once carbamic acid is formed. Gas evolution drives the reaction. As CO2 gas escapes from the reaction mixture, this shifts the equilibrium forward, ensuring complete conversion to the amine. Final outcome. So finally, we obtain a primary amine as the product, and importantly, one carbon is lost from the original acid in the form of CO2. That's a key feature of this reaction, which is a highly versatile intermediate. At the center, we have the isocyanate group, H3C, bond N, double bond C, bond O. Depending on the nucleophile present, it forms different products. When it reacts with an amine, RNH2, it forms a urea derivative through nucleophilic addition. With water, it undergoes hydrolysis to give a primary amine along with the release of carbon dioxide. And when it reacts with alcohol, ROH, it forms a carbamate. So the key idea is that the isocyanate group acts as an electrophile, and the type of nucleophile determines the final product formed. This slide highlights the applications of the Curtius rearrangement, a powerful reaction that converts carboxylic acids into amines, amides, and related functional groups via an isocyanate intermediate. On the left, it was used by Woodward in the synthesis of triquinacine, showcasing its importance in complex hydrocarbon construction. In the center, the reaction plays a key role in the synthesis of the antiviral drug oseltamivir, Tamiflu, enabling an efficient one-pot transformation under mild conditions. On the right, it is applied in the synthesis of the natural product diavodiamine, where the isocyanate intermediate undergoes intramolecular cyclization. Overall, the Curtius rearrangement is valued for its mild conditions, functional group tolerance, and efficiency in building complex molecules and pharmaceuticals. This slide illustrates the multi-step synthesis of triquinacine, with a key highlight on the Curtius rearrangement step. Initially, the starting compound is transformed into a dicarboxylic acid intermediate. The crucial step involves converting the carboxylic acid groups using SOCl2 followed by sodium azide, forming an acyl azide intermediate. Upon heating, this undergoes the Curtius rearrangement, where the acyl azide loses nitrogen gas to generate an isocyanate intermediate. This rearrangement is significant because it involves a migration of the R group from the carbonyl carbon to nitrogen, forming a highly reactive isocyanate without changing the carbon skeleton. Subsequently, the isocyanate reacts with methanol to give a carbamate derivative, as seen in intermediate 3. This step not only introduces nitrogen functionality, but also prepares the molecule for further transformation. Finally, through additional steps, including dehydrogenation, the system achieves aromatic stabilization to form triquinacene. So, overall, the Curtius rearrangement is the key transformation that enables functional group conversion while maintaining structural integrity of the framework. This slide shows the synthesis of -oseltamivir, highlighting an efficient one-pot transformation. The starting compound contains multiple functional groups, including an azide, nitro, and ester group, which are strategically arranged on a cyclohexene ring. The key step involves treatment with acetic acid and acetic anhydride under room temperature conditions. During this process, the azide group is converted into an amine functionality through a Curtius-type rearrangement pathway, followed by in situ acetylation to form an acetamide group. This transformation is significant because it combines multiple steps into a single one-pot operation, improving efficiency and reducing purification steps. Subsequently, further transformations occur in 2 steps, leading to the formation of the final product -oseltamivir with a 57% overall yield. Overall, this synthesis demonstrates how careful functional group manipulation and rearrangement strategies enable the construction of complex antiviral molecules in an efficient and practical manner. This slide illustrates the synthesis of +-diavodiamine, focusing on a key Curtius-type rearrangement and intramolecular cyclization. The starting material is a carboxylic acid-containing indol derivative. In the first step, treatment with DPPA and triethylamine converts the carboxylic acid into an acyl azide in situ. This is a crucial activation step for rearrangement. Next, in the presence of BF3.OET2, the acyl azide undergoes Curtius rearrangement, forming an isocyanate intermediate. This intermediate then rapidly undergoes nucleophilic attack intramolecularly, leading to cyclization and formation of a lactam structure, specifically an oxindol core. This step is highly efficient, giving a 94% yield, which highlights the effectiveness of this strategy. Finally, through subsequent transformations, the complex natural product +-diavodiamine is obtained. Overall, this synthesis demonstrates how Curtius rearrangement can be strategically used not only for functional group transformation, but also for constructing cyclic frameworks in a highly efficient manner. Thank you for watching. If you found this content helpful, please like, comment, and share it with your friends.